Alright, time for another math. Easy solution. Discuss introduction to Taylor Polynomials. Basically look at quadratic and higher degree approximations of functions. In my earlier videos I showed that you could approximate functions linearly using the equation of a tangent line. So if you set a graph x, y, if you were to draw a random curve like this, we'll call this one f of x. So basically if you were to approximate values close to, let's say, this value a, you could just draw the tangent line to it. I could derive the equation for it, and this was L of x. But if you wanna, so this one's this is f of a, and if you this approximation, you can get a good approximation for values close to this is f of x. Let's say here you could approximate it with this value here. But let's say you wanted a better approximation. Well, we could use quadratic or even higher degree polynomials. So you could determine an equation of a curve that kind of curves in like that, and then this would be a better approximation, and we'll call this p n of x. The n is the degree of it's the degree of the approximation. So p1 would be L of x, this is p1 of x, p2 would be quadratic and whatnot. So to start off, we gotta let's just do a quadratic approximation first. Let's just go quadratic. Okay, so quadratic approximation. We need the following to be true. So one, we need that we'll call this approximation, we'll call p2 of x. And then so we need to have p2 of a as to equal to f of a. That's the function we're approximating. And then the derivative at that point, a will be equal to f prime of a. So with linear approximations, this is all we need. This is just linear. And then we need to go one further to get quadratic. So 3, we're going to have p double prime, so the second derivative, or the change of the slope at a, equals the second derivative of this one. So now this is the quadratic, and just the first two is linear. And if we keep going further and further, it will start becoming higher degree polynomials. Okay, so now the equation of a quadratic equation you could write it as p2 of x is equal to a plus bx plus cx squared. So this is the equation, and then if we add our function, all we gotta do is find a, b, and c based on these following rules. But you could actually just rearrange this one to, let's write this as, it's easier to write it as a plus b x minus a plus c x minus a squared. So I'm just changing the form of it. This would be easier to show Taylor polynomials. I'll show that in a bit. So basically, if we had a function y equals f of x, and then we wanted to approximate this using this quadratic function here, we just need to just solve a, b, and c using these rules right here. So we know that p2 of a is equal to f of a. That's the stipulation we made. So this will just equal to a plus, and then if you plug in a in all these, those just cancel to become 0, and so we're just plus 0, and it keeps going on. So we just have 0. So f of a is equal to a, and now if we go do the derivative, we know that p2 of a is equal to f prime of a. And then this one equals derivative of this one 0. This one would just be b, so equals to b plus derivative there is 2c x minus a. And then if we plug in the a inside here, this becomes 0 here. Once we plug in 0, so we're just going to get f prime of a is equal to b. And then similar to do the second derivative, we just go f double prime 2 of a. This one just equals to f prime of a. Derivative of this one is just, well, this just goes away, and we're just left with 2c. And then just rearrange for c. This one will get c is equal to 1/2 times f double prime of a. Then we plug in these values inside this equation. We're gonna get P2, or the quadratic is equal to, this one is f of a plus f prime of a x minus a, then is 1 over 2 plus 1 over 2 f double prime of a x minus a. So there is our quadratic approximation. And as you can see from, if you just look at the first two terms, this one is just a linear approximation. This one's just L of x. Or if we write a P1 of x. So this is all we got to do here. But now, then if we get further, that's our approximation there. Okay, so now that we got this quadratic equation here, let's just get it to further degrees, or we get to the Taylor polynomial. This is basically where some guy named last name Taylor, he derived it. So basically, if you want to get further, let's call this Tn of x. Just replace the t with a p, I mean the p with a t, just so it's Taylor. So instead of settling with quadratic, we'll just go with, just write it like this: co plus c1. This is just constants. X minus a plus c2 x minus a squared, and then plus it keeps going on all the way to cn x minus a n. So this is just further and further. And then from here, if you want to solve for every single constant, we're going to do the exact same thing as over here. Then we're going to get further on, we'll see a pattern going on. So we know that, we know that t1 of a is equal to f of a. So then we just, remember we're always approximating f of x. So then here, we just plug in a here, these all become 0, so we're left with, this is just tn of a. Tn, not t1. And this one would equal to, well, the c is 0. And then, so that's what f of a is. Then if we take derivative, tn derivative of x, this just equals 2c1 plus 2c2 x minus a. And then plus, this one's going to be a 3 there, so 3c2, c3 x minus a cubed, plus etc. This one's going to be n cn x minus a n minus 1. And then this one, we know that tn of a is equal to f prime of a. Again, we plug in a in everywhere, so these all cancel. C1 is equal to, this one's c1. And this is exactly what we had at above. And then similarly, tn double prime a, this one's going to equal to this one right here, 2c2 plus this one, 3, no, this is I forgot to minus 2, this is a 2 here, 3, 2, so right there this is going to be 3 times 2 c3 x minus a. It keeps going on. This one's going to be right here n minus 1 cn x a n minus 2. This is the power of n minus 2. And then we know that tn double prime of a is equal to f double prime of a. These are the rules that we're setting, but now we're going to go further and further. And this one is equal to 2c2, so then c2 is equal to f double prime of a over 2. We'll do one more, then you'll see a pattern going on. Let's just go triple prime of a here is equal to, well, this one, this one just cancels out. This derivative here is 3 times 2 times c3 plus, keeps going on. We'll just ignore the 4 and whatnot. So this one right here, we'll get n minus 1 then times n minus 2, bring it down using power rule, cn x minus a n minus 3. So you can see the pattern here. It's n times n minus 1 times n minus 2 is just like here, 3 times 2 times 1. They're just getting smaller and smaller. So then right here we know that t double triple prime of n at a is equal to f triple prime of a, and this just equals to 3 times 2 times c3, because this put an a everywhere else, it becomes 0. yeah, so this one right here is just equal to, let's see, 3 is equal to f double prime of a over 3 times 2. Also, we'll put a times 1 here just so we could add factorial. So we're going to get f double prime of a is equal to 3 factorial. And this one is equal to 2 factorial as well. I'll do another math easy on factorial another time. And from this pattern you could see that, well, this one's f2 a divided by 2 factorial. This is f triple prime a divided by 3 factorial. And this one here is just, c1 here, or this one's also, this is f prime here. This is also, you could also write as 1 prime, which just equals to 1, so you could write it as that. And this one as well, this one could be equal to, well, divided by 0 factorial, is the same thing as this. So from this we could write the general formula for the constants. We could write ck equals to, well, f this prime of a divided by, well, this one is k factorial. So we know this. So this is just a general pattern that we determined here. Then if we plug this all into the final equation, we'll plug in the final equation, but this k prime just equals to, well, k times k minus 1 times k minus 2, etc., etc. It keeps going on. Oh, or that's what or you could, or just 1 times 2 times 3 all the way to k, or whatever k is. So now if we plug this all into the final equation, we get Tn of x is equal to, well, this is c0 is f of a plus f prime of a x minus a plus f double prime of a over 2 factorial, as is equals to x over a squared, and then plus keeps going on forever all the way till the end here. This is f of n of a over n factorial, which is this pattern we derived here, and this is x minus a to the n. And this equation here, this one is just called the Taylor polynomial. The nth, this is called the nth degree polynomial, Taylor polynomial centered at a. And also, point of interest, if a equals 0, then this would be called the Maclaurin series. And I'll show this in another video, more detail about this. So basically, now let's just do an example here. So if we want to approximate the function f of x is equal to cosine of x at, let's go a equals 0, and we know that this equation just looks like this. So then this is the equation, this is how the graph looks like of cosine. So now we know that, I showed in my other video, the linear approximation at 0 is just 1. This one is just L of x is equal to 1. So now let's just do further and further degrees of approximation. So let's just use this Taylor polynomial. Let's just do it up to, let's say 5 or 6 degrees, several degrees of approximation. So let's just start off with t of 0. This is just the first approximation. This one is just equal to, well, f of 0. And this one is equal to cos 0. This just equals to 1. And then the second approximation, or t1, this is x. This just equals to f of 0 plus f prime of 0 times x. And we know that, well, f of x is equal to cos x. So then we'll just get a pattern here. F prime of x is equal to negative sine of x. So let's say at x equals 0, this, we'll just write this one will be equal to 1. Then at x equals 0. This equals to, well, negative 0. And then similarly, we could keep doing a derivative here. F double prime of x, this one's equal to negative cos x. And then at 0, it's just, this one's negative 1. And then if we keep going, you'll see a pattern here. F double prime of x, this equals 2 sine of x. This is 0. And then f4, or no, Roman numeral 4, this is equal to cos of x is equals to 1. So our pattern here is 1, 0, this one is equal to 0, 1, 0, negative 1, 0. This one, we'll just call this a 0. Yeah, so the 0 or just the function. So we get 1, 0, negative 1, 0, 1. And then you can see from this pattern, 5, we'll just write 5 here. This just equals to 0. And then f6. This is x, this just equals 2, well, negative 1. And so on. So then from here we could just write out the Taylor polynomials. So then this one is 0 here. 0, so we're just left with 1. And then now if we write out the other one right here, so t2 of x, this one is just equal to, well, 1 plus 0 plus, or minus now, minus f double prime of 1, that's this one right here, divided by 2, this is just x to the 2. And then if we go t3, this one just equals this as well. This just equals to this one above. So we can ignore all of the odd numbered ones and just look at the even ones, because this one is the same here. So we only need to worry about, well, t4 of x, this one's equal to 1 minus 1 over 2 x squared, plus this one is 1. Yeah, this is always going to be a 1, so x4 over 4 factorial. This factorial is also equals 2, they're interchangeable. And then similarly t5 or t6 of x is equal to 1 minus 1 over half squared plus 1 over 4 prime x4 plus x6 over 6 factorial. So now if we wanted to graph all this out in Google Calculator, okay, so now if we were to graph out every single one of these approximations with cos x, just see which one is a better function. So cos x, this one just looks like this. And then let's just zoom in there. So now we want to graph out, well, the first one is just 1. The first approximation we had, the just linear one. So we could graph 1. This one is, well, that just looks like that. And if you were to zoom in, you see that, yeah, it's somewhat close to it, only at the beginning there. So now let's just see how these curves look out. Let's go with this one is the 2nd degree, or 4th degree, I think. Yeah, this one would be the 2nd degree, 1 minus 2 times x squared. Just graph this out. Yeah, I just change this up. So 1 minus x to the x squared divided by 2, same thing. So if you zoom in this one here, I'll just make this a bit bigger here. So we know the pattern here. Just it just goes even x4. This one, this one is, forgot the minus here, right here. This one's actually a minus because it alternates 1 minus x plus minus. Yeah, and if you zoom in there, you'll see that. Zoom in out a bit. Yeah, this one is really close to the sine one. The yellow one's right here, so it's really close to the cosine function right there. Then let's just do this one more here. 1 minus x squared divided by 2 plus 1 divided by 4. That's a factorial right there. So just write factorial times x to the 4. And this one, yeah, it's it's a parabolic. It goes up and down like as it should. And as you can see, it's really close here. We'll just zoom in. But yeah, as you can see clearly that the higher degree polynomial, it gets closer and closer, because you can see that the yellow right here, this one is the second degree, this is the fourth degree is much closer here, and then it tailors off to the end there. And yeah, what also happens is as you go on to infinity, it actually becomes really close to all of this. Let's just add further points to this one. 1 minus, this one is x to the 6 divided by 6 factorial. Yeah, and this part here is closer all the way up to here. Let's just keep going further. Plus x to the 8 divided by 8 factorial. And now it's going up. Yeah, so now as you can see, the green one is going up back to this one, so it's almost following a quadratic, I mean a trigonomic function like cosine. So if you keep going on further, this becomes pretty ridiculously close. 10 factorial. So there you go, it's almost going looping down again. So, and just add another term here. Divided by 12 factorial. So now it's getting closer up to the top. So it's really close to the beginning ones, and then it's getting closer and closer there. Let's just zoom in there. So yeah, this is pretty amazing what you can do with Google Calculator, and also this Taylor Polynomials, how accurately you could approximate all functions, and this is pretty amazing. Well, it's all for today. Hopefully you learned about Taylor Polynomials and how you could approximate basically any function as you go closer, like just go more and more terms. And also remember to do this so you get the pattern of the derivative, and it makes it much easier to get the polynomials here. Well, it's all for today. Hopefully you learned, and stay tuned for another math